D block elements, D and F block elements. Yes, giving you a, oh, disgusting. Yes, it is disgusting. But I think, we can sum up, give this entire chapter a good look with this quick revision. So let us start without wasting time. Let us start with the revision of D and F block elements. Exams are very near, and now you need to know everything at your, everything has to be on your fingertips. Let us start with the memory map. We have the 3D series of elements. We have the 3D series of elements. We have the 4D series of elements, the 5D and the 6D. So if you know the D block elements, why they are called the D block elements? The elements, the last electron is filled in the D orbital of the penultimate orbital. That means, if you take scandium, the atomic number of scandium is 21. So it's nearest to argon. So we have 3D1, 4s2. So the penultimate orbital is D. So that is why it's called, these are the D block elements. So we have the 3D series of elements, like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So if you want to know the mnemonic, science teacher very cruel, मांगे fees, कोई नहीं QG. मतलब कोई नहीं देता है fees QG. So scandium to zinc. So this way, you can learn the series of elements. Usually you do not require the series. 3D series is the only series that you require, and after that you require the third group. So you have scandium, yttrium, lanthanum, and actinium. And these are the elements. So, for example, I have made a small mnemonic to remember these elements, which is my sky lark. So this way you can go on making your mnemonics. So we have the fourth group as titanium, zirconium, hafnium, rutherfordium. Fifth group with vanadium, niobium, tantalum, dubnium, chromium, molybdenum, tungsten, seaborgium, manganese, technetium, rhenium, bohrium, iron, ruthenium, osmium, hassium, cobalt, rhodium, iridium, batrinium, nickel, palladium, platinum, sturdium, copper, silver, gold, rogentium, zinc, cadmium, mercury, and copernicium. This is Cn. So this finishes 3 to 12, the elements. I have given you all point-wise. These elements are known as transition elements because why? In the periodic table, these elements are in between the S block and the P block. So you have the S block elements on the left and the P block metals on the right of the periodic table. So this comes in between the S and the P. That is why they are called the transition elements. So in this group, the last electron, it enters into the S suborbit instead of the D suborbit of n-1 orbit. So that is why they are called the D block elements, because the penultimate shell is filling up the D subshell. The general electronic configuration of this D block element n-1 D 1 to 10 ns2. So if you want, you can just write the electronic configuration as n-1 D 1 to 10 ns2, which is the general electronic configuration pertaining to 3D, 4D, 5D, and 6D series of elements. Going on to trends. If we speak about the atomic radii, the atomic radii in the period, the atomic radius first decreases with the increase in atomic number up to the middle of the period and then becomes constant at the end of the period, which shows a slight increase. For example, if you take the 3D series, zinc will show a slight increase in the radii because of full-filled D subshell. Because of interelectronic repulsion, the shell shows a slight increase. So in this series, the size chromium, manganese, iron, cobalt, nickel, and copper is also the same. All right, chromium, manganese, iron, cobalt, nickel, and copper is almost the same. And this is due to what? Due to screening of incompletely filled D orbit in the n-1 subshell. In the second series, you have ruthenium. You can just go back to the table, check it out, and you can see that in the second series, the size of ruthenium and rhodium is almost the same. Once again, why is it so? Because of the screening effect. All right, and in the 3D series, the third series, the size of osmium and iridium are almost same, because of something called lanthanoid contraction. I'll discuss these eventually. Next, if we go along the group, the atomic radii increase due to the increase in the number of shells. The atomic radii will increase from the 3D series to the 4D series, but the atomic radii of the 3D and the 4D series, 3D and 4D series are almost the same. Lanthanoid contraction. So, because the reason I've given it here, this is 4D and 5D. So, this is due to the inclusion of the 14 lanthanoids between lanthanum and hafnium, that the size of hafnium and zirconium is almost the same. Even the elements of 5D series except lanthanum have nearly the same size due to lanthanoid contraction. Going on to the next one, the metallic character. All these, from the name itself, you can understand that these metals have lattice type structure, and the metal bonding is due to the presence of ns electrons and unpaired electrons in the d suborbit. जितने ज्यादा unpaired electrons रहेगा उतना ज्यादा interatomic interaction रहेगा, और जितना ज्यादा interatomic interaction रहेगा उतना strong metal bonding रहेगा. All right, so metal bond strength increases with the number of unpaired electrons. Copper, silver, and gold are known as noble metals, as you know, because they have less reactive properties. Zinc, cadmium, and mercury, they are known as volatile metals. Mercury is a liquid due to weak metallic bond, and chromium, molybdenum, and tungsten are very hard metals because of the strong metal bonding and having a very high melting point. So speaking about melting and boiling points, these elements have very high melting and boiling points. We just mentioned chromium, molybdenum, and tungsten are very hard metals because they have very high boiling points, melting points. And melting point increase with the increased number of unpaired electrons, except manganese, technetium, they have low melting points. Note it down. Tungsten has the lowest melting point. Now manganese has lowest melting point due to having a typical metal structure. So manganese and technetium have very low melting points. That is because though they have 5 unpaired electrons, but they have very weak metal bonding, right? They're extra stable. So they have very weak metal bonding. They have weak metal bonding, they're extra stable, and that's the reason they have low melting point. And even zinc, cadmium, and mercury have very low melting points because of the full-filled d orbital. The interatomic or metallic bonding is missing, and hence the melting points are very low. Going to the enthalpies of atomization. Enthalpies of atomization, again, it's very high due to strong interatomic interactions. The ionization enthalpies, if we speak about the ionization enthalpies, they increase from left to right in the series. The ionization enthalpy increases from left to right in a series. The first ionization enthalpy of zinc, cadmium, and mercury are very high because of the fully filled configurations. So whenever you have a fully filled configuration, naturally it will be very difficult to disturb the D10 configuration. So naturally the energy with which you will take out the electrons will be very high. Chromium and copper show unusually high values of second ionization enthalpies. So what will happen for chromium is that, so for chromium, we have the electronic configuration as argon 3d5 4s1. So chromium naturally will resist in giving out the second electron because of the half-filled d5. Same with copper also. Copper also, it has got electronic configuration argon 3d10 4s1. So both will resist the disruption in the D5 and the D10 configuration. So naturally, the second ionization enthalpies will be high. All the transition elements, excepting the first and the last member of this series, first member like scandium or yttrium or lanthanum or actinium, they do not show variable oxidation states because of the difference in energy between the n-1 d and the ns orbitals is very little, and the electrons from both the orbitals can be used for bond formation. So all the first and the last member of this series, they do not show variable oxidation state because, if you say zinc will only lose 2 electrons. Scandium will have a tendency to lose 3 electrons. So the variable oxidation state of +2 be here, +3 be here, that is rare with the first or the last element of the series. So the highest oxidation state of the transition elements are but found in the fluorides and oxides, and the ability for oxygen to stabilize the high oxidation states exceed that of fluorine due to the ability of oxygen to form multiple bonds. Oxygen can form a multiple bond with any transition element, but fluorine can have only one bond with a metal. So that is why, the higher oxidation states are more stabilized by oxides more compared to fluorides. The compounds in the +2 and +3 oxidation states are mostly ionic. Remember that. Okay. That means they would be able to lose, the metals will be able to lose 2 or 3 electrons to give rise to the +2 or the +3 oxidation state. But the rest will prefer to share electrons and give rise to covalent compounds. The highest oxidation state is equal to the total number of S and the D electrons. So the oxidation states will increase from scandium to manganese because of the increase in the number of unpaired electrons, and then decrease to zinc because the number of electrons keep on decreasing. Going on to the M2 plus M standard electrode potential. That means E naught M2 plus M do not show regular trend because of the irregularities in the ionization enthalpies and enthalpy of atomization. All together is responsible. All right. That means if I'm speaking about the electrode potentials, I'm correlating it with the ionization enthalpy and enthalpy of atomization. So the general trend towards less negative E naught value across the series is related to the sum of the first and the second ionization enthalpies. Okay. So E naught for manganese, nickel, and zinc are more negative due to stable M2 plus. That is D5 for manganese and zinc 2 plus D10, and they have high negative enthalpy of hydration. All right, for manganese, nickel, and zinc, what happens is that because of the stable configuration, and nickel because of the negative enthalpy of hydration, there is negative electrode potential. E naught of M2 plus M is low. And if you speak about the positive E naught for copper, it is due to the low hydration enthalpy. Okay. If we go on to the M3 plus M2 plus trend, it again shows varying trends. Why? The value for zinc and manganese due to the stable D10 and D5 configuration, they would resist a M3 plus configuration. So that is why the values for zinc and manganese, the M3 plus M2 plus reduction potential would be high. But the values for iron and scandium likes to lose all the 3 electrons and go to the argon configuration. So it would prefer to go to the +3 state and become stable. Same with iron. Iron, if it loses the 3rd electron, it would become a D5. So naturally, the values M3 plus, M2 plus for scandium and iron would be low. And the low value of vanadium is due to the stability of the half-filled T2G in V2 plus configuration. Let me explain this to you all. So if we take vanadium, atomic number 23, electronic configuration argon, 3D3, 4s2. So if both the electrons are removed, you are left with V2 plus. So with V2 plus, it has a 3D3 which is attributed to half-filled T2G. That means T2G3 configuration exists. So that is why the low value of vanadium persists. the low value for the electrode potential for vanadium persists. Going on to the next property, the formation of colored ions. You know that all these compounds, be it the solid state or the aqueous solution, they have if they have incompletely filled d orbitals, which split into a lower energy like T2G, EG. As you've learned, the crystal field splitting happens. So if the electron jumps from the lower orbital, lower d orbital to the higher d orbital, that means there is a split in the energy between the two d orbitals. On absorbing visible light, the electron will absorb visible light. The electron would absorb that energy, jump to the higher d orbital, and then it wouldn't remain there permanently. It would again jump down. So jumping down, it would give out energy in the form of light, which would appear as the light of that particular ion, be it in this ion or in the solid state. Okay. So going on to the next, which is formation of complex compounds. You know that transition metals, they have high nuclear charge, small size, high charge to radius ratio. So because of these properties, high nuclear charge, small size, high charge to radius ratio, also the availability of empty d orbitals, not only d, there would be empty s orbitals also, where the lone pairs of electrons from the ligand could be donated. Then they would form the complexes, and transition metals, that is why they form complexes. Remember the points, look into it. Formation of interstitial compounds. Interstitial compounds are the compounds which are formed on the lattice spaces of the metals on the surface. So small elements like hydrogen, boron, carbon, nitrogen, they can come and fit inside the interstitial spaces of these transition metals. So the compounds like titanium carbide, manganese nitride, and iron hydride, these are the interstitial compounds which could be formed on the surface of the transition metals. The last property, alloy formation, you know that these transition metals, because they have got similar atomic sizes, if they have similar atomic sizes, they have a tendency to form alloys. And what could happen is that in one lattice position, one metal could replace the other metal. So it gives a solid solution which is smooth, and hence alloying happens in transition metal compounds. Okay. So moving on to the compounds of transition metals, you know that oxidation states right from +1 to +7 is available. +1 to +7 oxidation states are available for the transition metals. And their ionic character will decrease with the increase in the oxidation state. All right. So as you know, as the metallic, so acid character increases as the oxidation state increases. So I have given these examples where MnO is basic. It can behave as a base, or it is ionic. Because it is ionic, because let's put it that way, because it is ionic, it is basic. And the rest, Mn3O4, Mn2O3, MnO2 are amphoteric, where the manganese have higher oxidation states, and Mn2O7, where manganese is in the +7 oxidation state. Because it's a covalent compound, it is acidic. Okay, now going on to the next one, which is to discuss the preparation of potassium dichromate. Whatever is there in the syllabus, I'm trying to compress it under one heading, and you can take this and read it as a quick reading, because most of the questions which you will get will be pertaining to these topics only. So going on to potassium dichromate, its method of preparation. So it can be prepared from chromite ore. What is chromite ore? FeOCr2O3, or you can write it at FeCr2O4. So you take FeCr2O4 and add the sodium carbonate and oxygen. Add the sodium carbonate and oxygen, you get sodium chromate along with Fe2O3 and CO2. Yes, if you ask me, you have to balance equation. Yes, without balancing, your marks would be deducted. Reduced. Yes, I mean it. So try to write equations in a balanced manner whenever you tackle with inorganic chemistry. So sodium chromate, what are we trying to do? We are trying to prepare potassium dichromate. Potassium dichromate, why? Because it's a very important lab reagent. It is used as an oxidizing agent in organic chemistry and everywhere else. So that is why the importance of potassium dichromate and its preparation has to be known. So first step to prepare potassium dichromate is to start from chromite ore. What is chromite ore? FeO.Cr2O3. This is one way of writing it, or you can write it as FeCr2O4. You add sodium carbonate and oxygen, you get sodium chromate along with the side products, which is Fe2O3 and CO2. And sodium chromate you acidify with sulfuric acid. You would get sodium dichromate with the side products as sodium sulfate and water. And sodium dichromate is to be converted to potassium dichromate. So add potassium chloride there. So there would be an ionic exchange and you would get potassium chromate, dichromate along with NaCl. And what about the color? It is, it's important to remember the colors. At least know that it's orange red in color, because if you are given a para-based question, you would be able to understand, like this orange red colored crystalline substance is nothing but potassium dichromate. So on heating, it strongly decomposes. To give oxygen. So K2Cr2O7, it would give K2Cr4 along with Cr2O3 and oxygen. Okay, so now this conversion, or we can call it this interconversion, where you have potassium dichromate and you give it a basic condition, it would change to potassium chromate. Potassium dichromate, I have written this ionic equation for you. Cr2O7 2 minus in presence of OH minus. It gives you same. It's like the top equation, but it's written ionically. It gives you CrO4 2 minus along with H2O. And you acidify chromate. You get your dichromate. So remember, chromate is yellow in color and dichromate is orange in color. Okay, you also have the preparation of potassium permanganate. So how is potassium permanganate prepared? From MnO2. And what is MnO2 called? Pyrolusite. All right, it is called pyrolusite. So that also you take in the presence of a base, potassium hydroxide. What did you use for preparing potassium dichromate? Sodium carbonate. And here you use the base, potassium hydroxide in presence of oxygen. You get potassium manganate. K2MnO4 is potassium manganate. This, in case you expose the pyrolusite ore to potassium carbonate in presence of oxygen, you again get potassium manganate, which is green in color, along with CO2. Okay, you expose this potassium manganate to chlorine, you get potassium permanganate, which is purple. There are a lot of methods which are available. There is also one method available where you fuse it. You take potassium manganate and you do an electrolytic oxidation in alkaline solution. Electrolytic oxidation in alkaline solution. That also gives you permanganate. Okay. So going on to the reactions. What happens if potassium permanganate is exposed to basic solution? If it's exposed to basic solution, potassium permanganate when exposed to basic solution gives you potassium manganate. So these are interconvertible. Change the pH of the solution and the manganate converts to permanganate. Permanganate converts to manganate. So this is how it happens. Look at the reaction where potassium permanganate reacts with acidic solution. It gives rise, you have a lot of redox reactions. So yes, you have to know when potassium permanganate is left in acidic medium, what happens? It converts to potassium hydrogen sulfate, a complex manganese sulfate and water. This manganese sulfate along with water changes to Mn2O7 along with H2SO4, dimanganese heptoxide. All right. it gives you Mn2O7, and Mn2O7 on heating, it gives you MnO2 and oxygen. So these were a few reactions of potassium. Yes, redox reactions pertaining to potassium dichromate and potassium permanganate. This reaction where you can see that I have just summed it up together. I minus, if you have in presence of acidified potassium dichromate, it will get converted to I2 or oxidized to I2. H2S will get oxidized to sulfur. SN2 plus will get oxidized to SN4 plus, and Fe2 plus will get oxidized to Fe3 plus. Okay. So this finishes the balancing of the redox reactions. We have a small test which is called the chromyl chloride test. And what is it all about? When you heat potassium dichromate with potassium chloride and sulfuric acid, you get CrO2Cl2 along with the side product, which is KHSO4 and H2O. I've picked up this reaction, you know why? Because ITARD reaction, we use this chromyl chloride as an oxidizing agent. So that's the reason I picked up this equation, just to give you an applied question. For MnO4 minus an acidic medium with 5 electrons, giving you Mn2 plus and H2O. So here also, this is one half equation, and the second half, you can use it for I minus getting oxidized to I2. See, it's repeating. Same thing dichromate had also done. Fe2 plus is converted to Fe3 plus. C2O42 minus, the oxalate anion, it's converted to carbon dioxide. S2 minus coming from H2S to sulfur. SO3 2 minus is converted to SO4 2 minus. NO2 minus is converted to NO3 minus. And this is how it goes. So now there is a small difficult question with potassium permanganate, and that is sometimes you are given the I minus, but the medium, notice the medium is neutral or faintly alkaline. So that time MnO4 minus changes to MnO2. Remember, not Mn2 plus. Look at the condition. Judge. If it is neutral, right, the side product is MnO2 and not Mn2 plus. In case MnO4 is behaving as the oxidizing agent. In that case, the I minus gets oxidized to iodate, IO3 minus, the S2O3 2 minus, the persulfate, it gets converted to sulfate, and Mn2 plus gets converted to MnO2. So this is how you are to take up this redox reaction. Okay, so the redox reactions are asked in such a way that the right side, it's a blank, you have to fill it up. So that's why I've summed it up, note it down, pause the video, note it down, and then things will become easy. Yes. Let's go to the next topic. Oh, yes, I am done. I'm actually done with the D block elements, and now for the F block elements. So you know that the F block elements start with cerium. The F block element starts with cerium, atomic number 58. Preceding cerium is lanthanum, which is a D block element, atomic number 57. You can see the electronic configuration is written for you. It is 5d1, 6s2. So because the electrons fill up the D shell, it is not an F block element, it's a D block element. So because cerium is preceded by lanthanum having similar kind of configuration like 5d1, have you noticed? It is 5d1 for cerium. That is the reason, after lanthanum, all these elements with 5d1 configuration persist. So that is why they are called the lanthanoids. There has been some observations about the switch of the electrons from D to F. So I have listed it for you. Pause it, have a look once. So whenever you see, say we are trying to figure out the electronic configuration of praseodymium, then what happens is that then the +3 oxidation state and +4 oxidation state persist. So you will understand that the D electrons switched, the D and the 5D and the 4F are degenerate. They are having nearly similar energy. So the electron can jump from the 5D to the 4F subshell. Okay, so you get 4F3 configuration, neodymium It's very easy to remember. See, whenever you have F1, F3, F2 is missing. So F1, F3, F4, F5, F6, F7. Yes, only F1 has the 5D filled up. So this is the electronic configuration. Then after F7, again we have 4F7, 5D1, 6S2. Do not disturb, do not forget to insert the electron in the D, because you would like to leave gadolinium with a half filled F. The full capacity of F is 40. So leave F with half filled, 7 electrons. So leave gadolinium with 4F7, 5D1, 6S2. Then after F7, F8 is missing. F9, F10, F11, F12, F13, F14. Yes, and then comes the last element, which is lutetium, which is 4F14, 5D1, 6S2. So you have your own, this is my, you can remember your own mnemonics. So we have lanthanum, cerium, praseodymium, neodymium, promethium, samarium. So I can give you a small hint, and I call this as my C Prasad. Cerium is C Prasad and yes, C Prasad and Pamsam. So this is how it goes. So you can make up any damn story of yours and remember this table. Yes, and most of the things are cracked if you remember the atomic number and the oxidation state. So have this near you before your eyes and half your job is done. And how much marks do you think F block elements questions will have? Hardly 1 or 2 marks. Okay, so the stress would be definitely less. Don't be so stressed. Here, these are the actinides. Actinium, is having 6D17S2 configuration. So because these elements fill up the 6D subshell like actinium, so these are called the actinides. Not all of them, and these are all radioactive or man-made elements. If you ask me, in the lanthanoids, are there any radioactive elements? The answer is yes. Promethium, PM. That was the only element amongst the lanthanoids which is radioactive. Let me write it down. In the 4F series of elements, I just forgot to mention, in the 4F series of elements, the only radioactive element is promethium. And in this series, all the elements are radioactive. All the elements are radioactive. Okay. So let's go on to the elements. Thorium, again 6D27S2. So here, weird things happen. They're radioactive. They have a short half-life, so most of the studies have not been done. So amongst those, a few known things, they have been listed down. So we have the elements as actinium, thorium, proactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. So you can just put this table near you. I've listed out the oxidation states also. Just keep it near you. Glance at once. Thorium, 5D, 6D2, 7S2. For proactinium, you have 5F2, 6D1, 7S2. And then uranium, yes, I don't expect these electronic configurations to be asked, but nonetheless, just record plutonium having +7 oxidation state from +3 to +7, neptunium from +3 to +7, lawrencium +3, actinium +3. And the rest, if you have noticed, all the elements have +3 oxidation state, all the elements. So you can make out that the +3 oxidation state is the most common oxidation state, not only for actinides, even for lanthanides. Okay, if you want, you can pause. You have your lanthanoids. The lanthanoid starts with cerium, atomic number 58. To lutetium, atomic number 71. So cerium to lutetium, I've already listed. If you want, you can learn it by heart. So if we discuss the chemistry, if you know the electronic configuration, you would be able to handle most of the questions related to that. So going on to the first one, which is oxidation state, listed here on the left, oxidation state. So let us discuss the oxidation state. The most common oxidation state for all the lanthanoids, be it the actinoids also, lanthanoids, it is +3. And why so? If you know the most highest common oxidation state, or the metals tend to lose at most 3 electrons, and after that losing the 4th electron is difficult. It would prefer to share electrons. So same is the case. Most of they are abundantly filled with electrons, where in the S, in the D, in the F subshell. So they can keep on losing electrons, but no, they would prefer to lose 3 electrons. Let us see, so why is it so? Most of the common oxidations is +3, and there are uncommon oxidation states like +2 and +4. We can easily figure it out. Let us try. Cerium, atomic number 58. Let's write down the electronic configuration of cerium. It is closest to xenon. Xenon's atomic number is 54, 55, 56, 57, 58. We need to put 4 more electrons. So after you are done with xenon, then you have 4f1, 5d1, 6s2. Yes, so you have 54, 55, 56, 50, 54, 55, 56, 57, 58 electrons done. So you can just figure it out that here the most common oxidation state expected is +4. Why? Because it will become a xenon configuration. Yes. Similarly, you can pick up an element of your choice like what? Lutetium. Yes. If you have correctly guessed it, very good. So let us take up lutetium. The electronic configuration of lutetium is xenon, xenon, 4f14, 5d1, 6s2. So yes, here you can figure out that, so the atomic number is 71. You check it out. So if it loses the 3 electrons, 2 from S and 1 from D, you land up with a +3 oxidation state for lutetium. Yeah, because you have a full-filled F14, and that's definitely wanted. So you have, I've given an explanation about the +3, I've given you an explanation about the +4, and you can figure it out for yourself, seeing the electronic configuration. What is the which element can have the +2 oxidation state? Let's go on to the oxidation state of cerium +4. If you have cerium +4, it will act as an oxidizing agent because it will tend to get reduced to the common oxidation state, which is +3. Europium +2 and ytterbium +2 will act as strong reducing agents because they will tend to get oxidized to the europium 3+ and ytterbium +3 oxidation state. Like all other elements, these elements, be the lanthanoids, they will, when exposed to moist air, they will burn in oxygen and form the respective oxides. Just like your DD transition happens in the lanthanoids, you have an FF transition. Okay, you have an FF transition which is happening in phenoids, giving rise to color. So if you see that there are any of these lanthanoid compounds are colored, you know it is due to the FF transition which happens back and forth. And definitely if it is F0, the FF transition will not happen, or for F14, the FF transition will not happen. So those compounds are colored. Going on to the next one, we'll go to the magnetic properties. So we have finished with colored ions. We have discussed oxidation states. We have finished the action of air. We have finished the colored ions. Let's go to the magnetic properties. Now these compounds are paramagnetic if they have unpaired electrons, and they are diamagnetic if they have no unpaired electrons. What about reducing agents? If they lose electrons, they could be reducing agents and tend to, yes, they tend to get oxidized. The electropositive character, they're highly electropositive because they have low transition energies, low enthalpy of ionization. They tend to form alloys. And why do they tend to form alloys? Because these elements are having nearly similar sizes. So they can exchange each other in their lattices. So hence alloys are formed. They do not have that much tendency to form complexes, do not have. Why lanthanoids do not have? It's just the opposite of the transition elements which we have just done. So here they do not have much tendency to form complexes ions due to low charge density. So you understand that if you are allowing complex formation to happen, they should have high charge density, and because of their large size. So in opposition to transition elements, they have small sizes and they have high charge density, and that is the reason to form complexes. All right, so But if they form complexes, the tendency to form complexes and the stability increases with increasing atomic number. If you know the atomic number increases from left to right across the 4F series, the sizes will decrease because of the contraction, because of the increased nuclear charge and the contraction. So the stability of the complexes increases. Going on to the next point, let's go to lanthanoid contraction. I just spoke about this, that if we proceed from left to right, from lanthanum to lutetium, there's a increase in atomic number, and if there's an increase in atomic number due to increased nuclear charge, the atomic radii decreases. And that is true not only for the elements, this is true even for the ions. Okay, so let us write down the point. Please stop, pause the video, write down once only. You write down the reason and you will remember it. I bet you will remember it when if this question is asked in the exam. And what is the reason for this contraction is due to the addition of new electrons in the F subshell and the imperfect shielding of one electron by the other in the F orbital. So there is a greater or an increased nuclear charge. Okay, hence there is a contraction in size because of the screening effect. Okay, so this is the reason for the lanthanoid contraction. Pause the video, write it down once, and you will exactly remember the language. If you write an imperfect language, there are, you are not able to put across your point to the teacher, to the examiner. You get it wrong. Okay, so we have learned about lanthanoid contraction. Now let's go to the consequence. What is the consequence of lanthanoid contraction? The separation of some of the elements is very difficult, because there are very small differences in properties, and the 4D and the 5D series of transition elements have almost the same radii. And which two elements have the same radii? Zirconium and hafnium. These are the elements which have nearly the same size. Yes, zirconium and hafnium, they are also called chemical twins because they have almost similar properties and almost similar radii. And the uses of lanthanoids is to prepare misch metal. Yes, to prepare misch metal, which is an alloy of any of the lanthanoids, 95% any lanthanoid metal, 5% iron, and traces of, I call it my sakal. Morning, good morning. Yes, so I call it my sakal, is S carbon, kal, CaAl. So sakal is present in traces, and it is used to make tracer bullets, shells, and lighter flint. Okay. Now to the characteristics of the actinoids. Once again, it's similar to if you have learned lanthanoids. I don't think so you have to really go in depth for actinoids because things are nearly similar. Like lanthanoids, ionic radii decreases regularly across the series, and that regular decrease is called actinoid contraction. And again, this is due to greater, due to poor shielding of the 5F electrons. The 5F electrons are beyond the 4F electrons, and so that is why the 5F orbitals, they extend in space beyond the 6S and the 6P orbitals. Or that is what causes a greater contraction in the radii. So like the lanthanoids, the actinoids also have a common oxidation state of +3. They have other oxidation states like +4, +5, +6, +7 also. And that you can check out just like the electronic configuration. Let us check out. The actinoids start from thorium, atomic number 90, and end with lawrencium, atomic number 103. So you can check up for thorium, which is having the electronic configuration radon 5F1, 6D1, 7S2. There is a lot of controversy regarding the calculated and the observed electronic configurations. You can just check up and you can see that because of the degeneracy or the less difference in energy between the 5F and the 6D orbitals, these electrons tend to jump, all right, from 6D to 5F. So sometimes you may see the electronic configuration written as 5F to 7S2. It is because of the degeneracy of the 5F and the 6D orbitals. So any one of them is correct. So in this case also, you can have a +4 oxidation state for thorium, as you can see, in order to have a radon configuration, and so on and so forth. And yes, because there is a small energy gap not only between the 5F and the 60, even of the 7S shells, they tend to have a large number of oxidation states. Okay, so let's go on to the next one. Here also, if you speak about the action of the acids or the alkalis or air, these elements which are silvery white usually tends to tarnish, get an oxide coating, okay, with oxygen or, you know, acids, and they are not attacked by alkalis and they are less reactive towards acids. If you speak about the lanthanoids, you know, the lanthanoids can react with oxygen to give the oxides, the chlorine to give the chlorides, hydrogen to give the hydrides, sulfur to give the sulfides, carbon to give the carbides. These are just addition reactions, so simple that we need not discuss about that at all. Yes. So here the reactivity, you know, is less known because all these metals are radioactive. Okay, so yes, it is less studied of, but whatever is studied, let's know about it. So here also, if you notice colored ions, okay, if you notice colored ions, it would be due to FF transition. Magnetic properties, they are strongly paramagnetic because of the high number of unpaired electrons. The densities are quite high. All actinoids except thorium and americium have high densities. If you want, you can just remember this part if it comes as an MCQ. Melting points and boiling points, however, there is no regular trend with the rise in the atomic number. The ionization enthalpies are low because the last electrons are very far away from the nucleus. So the electrons can be taken out easily. They are all strong reducing agents because they have a tendency to get out. They're metals. So metals usually will be strong reducing agents because they will have a tendency to lose their electrons and get oxidized. Yes, and metals are highly electropositive. So also nothing unique. It is everything that you know. And what are the uses of actinoids? Thorium, it's used in nuclear reactors that you must be knowing, in atomic reactors, and it's also used as a treatment of cancer. Uranium and plutonium, they're used as fuels in nuclear reactors. Okay, so going on to the differences between the lanthanoids and the actinoids, which is a pretty common question to be asked. Lanthanoids show +4, +2 oxidation state, along with the most common oxidation state, which is +3. In actinoids also, you have +4, +5, +6, +7, besides +3, the common oxidation state. In lanthanoids, promethium is only, one which is radioactive, promethium, which is radioactive, and all the actinoids are radioactive. These lanthanoids, they do not form oxocation. As we have learned, oxocations for transition metals, but oxocations do not exist for lanthanoids, but actinoids, they form the oxocations like UO2, 2+, etc., which has been shown. The compounds of lanthanoids are less basic. What happens? Why are they less basic? Because we are speaking about lanthanum hydroxide. The compounds of lanthanoids are less basic, but the actinoid compounds are more basic. And they have a tendency of complex formation less compared to the actinoids, which have a greater tendency for complex formation. So these are the important things that you need to remember. Let us wind up this session, giving you a few questions for self-practice. So explain the melting and boiling points of transition elements first increase and then decrease in the series. You can see the answer. I've written it down for you. Of the ions, scandium 3+, cobalt 2+, and chromium 3+, which ions will give colored aqueous solutions, and how will each of these respond to a magnetic field, and why? The answer has been given to you. Why most of the transition elements act as good catalysts. The answers have been listed down for you. What is meant by lanthanoid contraction? I've given you the answer. And what are the causes of lanthanoid contraction? I need not be with you. You hope this quick revision was helpful for you. Do not forget to like and subscribe. And thank you for watching.